Okay, today we're going to be discussing the negation of negations of quantified statements. All right, Theorem 3.2.1. The negation of a statement of the form for all x in D Q of x, the negation is that for there exists an x in D such that negation of Q of x, not Q of x. So put a negation on this, and it becomes this. So the negation of a universal quantified statement is a existential statement. Instead of for all x in D, Q of x is true, there exists some element of D in D such that Q of x is not true. So the existential statement is the negation of the universal quantified statement. This is the case without respect to the predicates and the domains of the predicate variables. Now, as you might expect, there exists an element in D such that Q of x, the negation of that is going to be a universal quantified statement with the predicate inverted. So if there is not an element in D such that Q of x is true, that means that for all x in D, Q of x is not true. So yeah. So negations of the following statements. Some examples here. Let's see here. For all P elements of primes, P is odd. What is the negation of that statement? For all p's and that are elements of the prime numbers, p is odd, which is a false statement. So what's the negation of that? How do you make it true? Well, inverting it, there exists a p in primes such that p is even or not odd. Oops. There exists an element in a p that's an element of the primes that is even, namely the number 2. So this is a false statement, so take the negation of it and you get the existential statement. There exists a triangle T such that the sum of the angles of T equals 200 degrees. Again, this is a false statement, so you negate it and you come up with a universal statement for all angles T, or triangles T. The sum of the angles of T does not equal 200. So, a little bit cumbersome to write out on the screen, so just do that verbally. Care must be taken to avoid mistakes when writing negations of the statement that are given informally. One way to avoid mistakes is to write them formally and then negate them. What about the statement, no politicians are honest? I'll refrain from political commentary at this point. But formal version, for all x in politicians, yeah. Oh no, it's. I thought I was spelling it wrong. And x is not honest. So that you write it out formally and then negate it to there exists a politician X such that X is honest. The informal negation would be some politicians are honest. Negations of universal conditional statements. Negation of universal conditional. All right. The form of negations of universal conditional statements can be derived from facts that have already been established. So, the negation of a universal statement, you would say you have a for all x in D, P of x implies Q of x. To negate it, you would, to negate that, you would have there exists an x in D such that P, if P, then Q of x is not true. But since the negation of a conditional can be rewritten in a simpler form with fewer parentheses, this becomes there exists a x in D such that P of x and not Q of x. If you remember from conditional statements that is the negation of the conditional. So this would be the form of the negation of the universal statement. There exists an element in D such that P of x is true and Q of x is not true. So that would be your negation. Let's see here. What is the negation of the following statement? A person P, for all persons P, if P is blonde, then P has blue eyes. So for all P in persons, P is blonde, implies P has blue eyes. What would the negation be? This example gives a little bit more clarity as to what the negation of a conditional, universal conditional looks like. There exists a person P such that P is blonde and P does not have blue eyes. So you can see that, there is the negation of all blondes have blue eyes is there is a blonde that does not have blue eyes. So you can see how the relationship between the original and the negation work there in informal language. Let's see here. The relation between the universal quantifier, existential quantifier, and or. Let's see here. We saw that the negation of a for all statement is a there exists statement and vice versa. These facts are analogous to De Morgan's law. The negation of an and is an or and vice versa. Universal statements are generalizations of and statements, and existential statements are generalizations of or statements. So, for all x in D, q of x1, q of, q of x1, and q of x2, and ... and q of xn. It's true for if it's a universal quantifier. That doesn't really make that really clear here. Let's see here. For all x in D, q of x is equivalent to q of x1, q of x2, etc. for all of the elements of D. Likewise, there exists an x in D such that q of x is equivalent to q of x1 or q of x2 or ... or q of xn. There exists statement is equivalent to a series of or statements for each element of D as the argument for Q. So you can see how if you were to invert this statement, you would get not Q of x1 and not Q of x2 and ... and not Q of xn. If you were to invert this and apply De Morgan's law, you would get this, which is the equivalent of the universal a universal quantified statement with the predicates negated. So you can see that there is a relationship between there exists the for all statements and sequences of ands and ors. Okay, what about the vacuous truth of universal statement? Oops, wrong button. Vacuous truth. Consider the statement that all the balls in a bowl are blue, when there are in fact no balls in the blue, in the bowl. Is this statement true or false? The statement, all the balls in the bowl are blue, but there are no balls in the bowl. It is only false if and only if the negation is true. The negation is there exists a ball in the bowl that is not blue. So, but the only way for the negation can be true is for there to actually be a non-blue ball in the bowl, and there isn't. So the negation is false, and the original statement is true by default. So, in general, for all x in D, if P of x, then Q of x it is called vacuously true if and only if P of x is false. If and only if P of x is false for all false. And my hand was getting ahead of my brain here. For all x. Remember, if the hypothesis of a conditional is false, then the conditional is true. Remember that? Vacuously true conditionals. The same is true for when it's applied to universal statements. Now there's we'll go through some variants of the universal conditional here. Some variants that you might remember some variety of. The contrapositive. For all x in D, not Q of x implies not P of x. Remember the contrapositive from conditional statements? It can be applied to universal statements as well. And these two are equivalent because the contrapositive here is equivalent to the original conditional. What is not equivalent is the converse. For all x and d, q of x implies p of x. That is not equivalent. Same with the inverse. For all x and d, not p of x implies not q of x. So this is equivalent. Not equivalent. So what is the contrapositive of the statement? If a real number is greater than 2, then its square is greater than 4. The contrapositive of that. If the number is less than 2, then its a real number is less than 2. Less than or equal to 2, then its square is less than. No, if the square is less than or equal to 4, then the number is less than or equal to 2. Negate and flip them. So the converse, this form here, if the square of a real number is greater than 4, then the number is greater than 2. So, and the inverse would be the, if a real number is less than or equal to 2, then the square of the number is less than or equal to 4. So, yeah. Necessary and sufficient conditions. Necessary and sufficient conditions. Definition. For all of x, R of x is a sufficient condition for S, means for all of x, if R of x, then S of x. For all x, R of x is a necessary condition for S of x, means if, for all of x, if R of x, if not R of x, then not S of x. Or equivalently, because of the contrapositive. For all of x, if s of x, then r of x. For all of x, r of x only if s of x means that it means for all of x, if not s of x, then not r of x. So let's write these out here. Sufficient condition. For all of x, d, if r of x, then s of x. Necessary is if not r of x, then not s of x. Not r of x, not s of x. Right? Yeah. Or equivalently, s of x implies r of x by the contrapositive. And the only if is for all of x, if r of x, then s of x. Yeah. Present each of the following as a universal conditional statement, but do not use the word necessary or sufficient. Squareness is a sufficient condition for rectangularity. How would you restate that without using the word sufficient? Squareness is a sufficient condition for rectangularity. So that would be, if a figure is a square, then it is a rectangle. Right? Being at least 35 years old is a necessary condition for being President of the United States. Seems like we had this one before. For all persons x, if x is younger than 35, then x cannot be President of the United States. Or the contrapositive, for all persons x, if x is President of the United States, then x is at least 35 years old. All right. Now, we get into statements with multiple quantifiers. All right. Actions suggested by the quantifiers are performed in the order in which the quantifiers occur. Let's see here. Let's say use the example of for all x in D, there exists a y in E such that P of x comma y. For every x in D, there's at least one y in E that satisfies the property P of x, y. To show that the statement is true, you must show that for every element in D, there's at least one element of E that satisfies the property. Because you do not have to specify the second element until after you choose the first element, you are allowed to have a different second element for each of the first elements you choose. The slides get into, this is, I believe, still 3.2. The slides use another Tarski's world example to demonstrate this concept. I leave it to you to look at the slides and follow the example, flip-flopping back and forth between the slides on Canvas to go through the examples. So interpreting statements with two different quantifiers. There's this version, the universal quantifier first, where your challenge is to allow someone to pick whatever element in D they wish, and then you must find an element in Y and E that works for that particular X. So now if the quantifiers are reversed, so say if there exists an X in D such that for all Y in E, P of XY, XY. So you pick a D that will work no matter, an element of D that will work no matter what Y in E anyone else might choose to challenge you with. Okay. Kind of a big example coming up here. Let's see here. Cafeteria line has 4 stations. Salads, main course, dessert, and beverage. Let's see here. Salad. Green salad. Fruit salad. Main course has spaghetti or fish. Dessert has pie or cake. And beverage has milk, soda, or coffee. Okay. So Uta takes a green salad, spaghetti, pie, and milk. So let's say Uta takes, what did I say? Green salad, spaghetti, pie and milk. Pie and milk. All right. Tim takes fruit salad, pie, cake, milk, and coffee. Fruit salad, fish, pie. Fruit salad, fish, pie, cake, and milk and coffee. And then finally, Yuan, or Yuan, takes spaghetti, fish, pie, and soda. Spaghetti, fish, pie, and soda. Now looking at this chart here, you can see what quantified statements are true or not. There exists an item I such that all students S chose I. Is that true or false? Which one? Pi. Okay. Yeah. There exists a student S such that such that all items I S chose I. There is a student that chose every item. False, exactly. There exists a student S such that all stations Z, there exists an item I such that Z, there exists an item I in Z such that S chose I. There is a student that chose at least one item from every station. True. Yeah, because, well, Uda is just one example, took 4 items, one from each station. For all students S and all stations Z, there exists an item I in Z such that S chose I. Every student, basically, translation would be every student chose at least one item from every station. False. UN didn't take a salad. Yeah, so, yeah. But you see how you do it in order. The quantifiers, as they appear, limit or expand your options and that sort of thing. So, translating from informal to formal language. Problems are often presented in informal language. Solving them often requires translating them into formal language. Redo the following statements in formal language. Every non-zero real number has a reciprocal. What would the formal representation of that be? For all, oops, I'm still in blue here. For all x in R non-zero, there exists a y in R such that x times y equals 1. See how that works? For every non-zero real number, there is a reciprocal. For all, there exists a reciprocal. For all non-zero real numbers, E, a real number V such that UV equals 1 is how they put it. There is a real number with no reciprocal. There exists a real number such that no real number is its reciprocal. You have to have the for all in there, and there exists in there. So it would be there exists x in R such that for all y in R, x, y does not equal 1. Translating informal language into formal language allows you to prevent ambiguity, allows you to be precisely clear about what you're trying to say and reason with. Now, negations of statements with more than one quantifier. You can use the same rules to negate statements with several quantifiers that you used to negate simpler quantified statements. Example, let's see here. The negation of for all x in D, there exists a y in E such that P of x, y. The negation of that, you would start with the first quantifier. So it'd be there exists an x in D such that And then after this, you would negate what's after that. There doesn't exist a y in E such that P of x, y. And then you would negate the second existential quantifier here. So you would have, there exists an x in D such that for all y in E not P of xy. So you do it in steps. Take care of the first quantifier and negate it, which in turn negates the second quantifier. Then you negate that second quantifier, which in turn negates the predicate. And the same is roughly true for, basically the same as with, if you start with an existential quantifier and you're negating the whole thing. Let me put some parentheses here so that you can be a little bit more clear. So, yeah, just break it down into steps. Don't try to do it all at once. You keep the steps simple. Slides use another Tarski's World example. I leave it to you to consider the example given. Now consider the following two statements. There exists a person X such that, for all persons X, there exists a person Y such that X loves Y. And the statement, there exists a person Y such that all persons X loves Y. The predicate is the same, X loves Y. But the order of the quantifiers is different. And it changes the meaning of the statements greatly. If the quantifiers, basically those statements translated to, for every person, there's one person that they love. Everybody loves at least one person. The second one is, there exists a person such that everybody loves them. Two totally different meanings of statements. If the quantifiers are of the same type, like there exists a person such that there exists another person such that X loves Y, you can switch the order of the quantifiers and it does not change the meaning if they are of the same type. So let's see here. In some areas, logical statements are expressed purely in symbolic notation, which is what I've been using up here. Symbolic notation. I don't use words like such that or there exists or anything like that. The disadvantage of fully formal notation is that because it is complex and somewhat remote from intuitive understanding, when we use it, we may make errors that go unrecognized when we make the translation from informal language to formal language. The advantage is operations can be made completely mechanically. The symbols for quantifiers, variables, predicates, and logical connectives make up what is known as the language of first-order logic. When you do things symbolically and leave the words out of it, it's easier to manipulate. You save time writing out sentences, that sort of thing. So carefully translate your informal language into formal symbolic language, such as this, and then do your manipulations, and then carefully translate back from the formal language into informal language. The slides give an example of programming in a interesting language called Prolog. Prolog is short for programming in logic. I have programmed in the language many years ago when it was in the early days of personal computers. Basically, you can symbolically make relationships with different data and derive new information from the data based on those relationships. Prolog isn't used much. If you can find a compiler for it, more power to you. But it is a fascinating language, and you can do a lot of different things with it. Let's see here. Do we have time to go through this? I think we'll call it a day at that. We'll do some arguments with quantified statements on Tuesday. So have a good weekend. See you next week.